Chien Shiung Wu was born in 1912 in Liuhe, a small town near Shanghai, China, during the final years of the Qing dynasty. Her father was a progressive educator who believed passionately that girls deserved the same educational opportunities as boys, a radical position in early 20th century China. He founded a school for girls in their village, ensuring his daughter received an education that was denied to most Chinese women of that era. Wu excelled in mathematics and science, demonstrating exceptional talent that marked her as extraordinary even among gifted students. She attended the National Central University in Nanjing, graduating at the top of her class in physics in 1934. In 1936, Wu traveled to the United States to pursue graduate studies, initially planning to return to China after completing her doctorate. She enrolled at the University of California, Berkeley, where she studied under Ernest Lawrence, the inventor of the cyclotron and future Nobel laureate. Her doctoral research focused on nuclear fission, the process by which atomic nuclei split apart releasing enormous energy. She completed her dissertation on the electromagnetic radiation emitted during nuclear reactions, work that demonstrated both theoretical sophistication and experimental precision. By the time she earned her PhD in 1940, she had already established herself as one of the most skilled experimental physicists in America. The outbreak of World War II and the Japanese invasion of China made Wu's return home impossible. She remained in the United States, taking a teaching position at Smith College and later at Princeton University. At Princeton, she became the first female instructor in the physics department, breaking gender barriers at one of America's most prestigious institutions. However, the systemic racism and sexism of American academia meant that despite her extraordinary qualifications, she could not obtain a permanent faculty position at a major research university. Her status as a Chinese woman in wartime America placed her under suspicion and surveillance even as her expertise became increasingly valuable to national security. In 1944, scientists working on the secret atomic bomb project at Columbia University encountered critical problems with uranium enrichment. The process of separating the fissionable isotope uranium-235 from the more common uranium-238 was proving far more difficult than theoretical calculations had predicted. Enrichment plants at Oak Ridge in Tennessee were producing material that mysteriously lost radioactivity over time, threatening the entire timeline for weapons development. The Manhattan Project desperately needed someone who understood the complex nuclear physics involved and could design experiments to diagnose the problem. If you want to discover more hidden scientists whose crucial contributions to history were deliberately suppressed, subscribe now and activate the notification bell so you never miss these remarkable stories of forgotten geniuses who shaped our world. The project directors reached out to Chien Shiung Wu, recognizing that her expertise in beta decay and nuclear spectroscopy made her uniquely qualified to solve their uranium crisis. Wu joined the secret program at Columbia University, one of multiple sites working on different aspects of atomic weapons development. She immediately began investigating the radioactive decay patterns in enriched uranium samples, conducting meticulous experiments to understand why the enrichment process was failing. Her work required extraordinary precision, measuring radiation levels and decay rates with equipment that was primitive by modern standards. She worked grueling hours in laboratory conditions that were often dangerous, handling radioactive materials without adequate safety protocols. Wu discovered that the problem was xenon poisoning, a phenomenon where a byproduct of nuclear fission absorbs neutrons and prevents the chain reaction necessary for both reactors and weapons. The isotope xenon-135 was being produced during the enrichment process and was absorbing the very neutrons needed to sustain nuclear reactions. This scientific finding was crucial because it explained why reactor designs were failing and why weapons-grade uranium required higher levels of enrichment than originally calculated. Wu's experimental work provided the data necessary to redesign the enrichment facilities and adjust the specifications for weapons development. Without her contributions, the Manhattan Project timeline would have been significantly delayed. Beyond solving the xenon problem, Wu contributed to understanding radiation detection methods and improving the purity of uranium isotopes. She developed techniques for measuring radioactive emissions with unprecedented accuracy, work that became essential to verifying the quality of weapons materials. Her laboratory notebooks from this period, many still classified for decades after the war, document hundreds of experiments and calculations. She worked alongside some of the most famous physicists in history, including Enrico Fermi and Robert Oppenheimer, though her name rarely appeared in official reports. The military security system surrounding the project meant that compartmentalization and secrecy prevented her from receiving recognition even within the scientific community. When the atomic bombs were dropped on Hiroshima and Nagasaki in August 1945, ending World War II, the public announcements credited the achievement to a small group of prominent male scientists. Robert Oppenheimer became known as the father of the atomic bomb, while Enrico Fermi, Niels Bohr, and others received public acclaim. The contributions of women scientists and minority researchers were systematically omitted from official histories of the project. Wu's role remained classified and unknown to the general public for decades after the war ended. Even within the physics community, few people understood the extent of her contributions to weapons development. After the war, Wu continued her experimental physics research at Columbia University, where she finally obtained a faculty position in 1952. Her most famous work came in 1956 when she designed an elegant experiment that disproved the law of conservation of parity, a fundamental principle that physicists had believed for decades. The parity experiment demonstrated that certain nuclear processes do not behave identically when viewed in a mirror, overturning assumptions about fundamental symmetry in physics. This discovery was so significant that the Nobel Prize in Physics was awarded in 1957 for the theoretical work suggesting the experiment. Once again, Wu's crucial experimental contribution was overlooked, and the prize went to her male colleagues Sung Dao Lee and Chen Ningyang. The pattern of Wu being denied recognition for groundbreaking work became a recurring theme throughout her career. She made fundamental contributions to nuclear physics, weak interactions, and particle physics that advanced scientific understanding. She trained generations of graduate students and became a respected mentor to young physicists. She published over 200 scientific papers and became the first woman to serve as president of the American Physical Society. Yet she never received the Nobel Prize that her experimental genius deserved, and her Manhattan Project work remained largely unknown. The reasons for Wu's historical erasure were multiple and overlapping. Gender discrimination in scientific institutions made it easier to credit male colleagues even when women did equivalent or superior work. Racial prejudice against Asian Americans, especially intense during and after World War II, marginalized Chinese scientists regardless of their achievements. Government secrecy surrounding the Manhattan Project meant that classified contributions could not be publicly acknowledged. The tendency to celebrate theoretical physicists over experimental scientists meant that those who designed experiments were often overshadowed by those who proposed theories. Wu's experience reflected the broader invisibility of women in the Manhattan Project. Thousands of women worked on atomic weapons development as scientists, technicians, and computing specialists. Women performed nuclear calculations, monitored radiation levels, processed chemical separations, and operated enrichment equipment. Yet the official narrative portrayed the project as an accomplishment of male scientific genius, erasing the essential contributions of female workers. This historical distortion persisted for decades, only gradually being corrected as classified documents were released and feminist historians challenged traditional accounts. Throughout her career, Wu navigated the complex politics of being a Chinese scientist in America during periods of intense anti-Asian sentiment. During the Cold War, Chinese scientists faced suspicion of communist sympathies and were sometimes denied security clearances or research opportunities. Wu maintained her connection to Chinese culture and scientific colleagues while establishing herself as an unquestionably loyal American scientist. She became a symbol of scientific excellence transcending national and racial boundaries, though this status did not protect her from discrimination. Her grace under pressure and refusal to be limited by others' prejudices made her a role model for minority scientists. Wu received numerous honors later in her career, including the National Medal of Science in 1975 and the Wolf Prize in Physics in 1978. These awards recognized her lifetime contributions to experimental physics, though they came decades after her most important work. Princeton University, which had employed her as an instructor but refused her a permanent position, eventually awarded her an honorary doctorate. Columbia University established a professorship in her name, and asteroid number 2759 was named in her honor. These recognitions, while meaningful, could not undo the professional injustices she experienced throughout her career. Chien Shiung Wu continued working and publishing research into her 70s, maintaining the experimental rigor that defined her career. She mentored young scientists, especially encouraging women and minority students to pursue careers in physics. She spoke publicly about the challenges faced by women in science and advocated for more inclusive academic cultures. Her commitment to scientific excellence never wavered, even as she acknowledged the systemic barriers that had limited her recognition. She passed away in 1997 at the age of 84, leaving behind a scientific legacy that continues to influence modern physics. Today, as we live in a world shaped by nuclear technology, both its destructive power and its peaceful applications in energy and medicine, we are living with the consequences of work that Chien Shiung Wu helped make possible. The atomic weapons that ended World War II, the nuclear reactors that generate electricity, and the medical isotopes used in cancer treatment all depend on understanding nuclear physics that Wu advanced. Every experiment in particle physics that tests fundamental symmetries builds on the work she pioneered. The story of the secret scientist behind the Manhattan Project is finally emerging from classified files and historical obscurity. Wu's contributions to the most significant military project of the 20th century deserve to be taught alongside those of Oppenheimer and Fermi. Her experimental genius solved problems that could have derailed weapons development and changed the outcome of World War II. Yet for decades, her name was deliberately excluded from historical accounts, her achievements classified or attributed to others. Chien Shiung Wu's hidden genius helped create the atomic age while facing discrimination that would have defeated less determined scientists. She proved that scientific excellence knows no gender or nationality, that experimental precision matters as much as theoretical brilliance, and that history must acknowledge all who contributed to transforming our world. Her story is not just about one forgotten scientist but about the countless brilliant minds whose contributions were suppressed by systemic prejudice and institutional secrecy.